Hello everybody and welcome to lesson 5 linear programming solution using simplex method in the case of maximization. Previously, as you remember, we have discussed about linear programming solution using graphical method. By the way, graphical method can solve linear programming having two decision variables. If the decision variables are more than 2, so we have to search another method to solve the linear programming. And today we are going to discuss about linear programming having 3 decision variables using simplex method in the case of maximization. Thus, our objective of today's lesson is to solve the linear programming problem having 3 decision variables in the case of maximization using simplex method. Let's get started. Before moving to our step-by-step discussion of simplex method, let's know what simplex method means. Simplex method is a general purpose linear programming algorithm that can be used to solve problems having more than 2 decision variables. If the problem has only 2 decision variables, we can alternatively solve using graphical method. By the way, simplex method can also solve a linear programming having 2 decision variables. But because a linear programming problem with 2 decision variables cannot be solved using graphical method, so simplex method is suitable to solve a linear programming having more than 2 decision variables. The simplex method is an iterative process. It is an iterative step-by-step process starting at some initial feasible solution, or we can say corner point usually the origin. Then each iteration moves to another corner point with an improved or a better solution, or at least not worse, value of the objective function. Our objective function with each iteration becomes improved. Iteration stops when an optimal or the last solution, if it exists, is found. If optimal solution is arrived, so our iteration step stops. And there are different variables like basic variables and non-basic variables when we are solving using simplex method. The basic variables can take any value other than 0, whereas the non-basic variables take the value of 0. Now let us start our discussion, that is the steps of simplex method in the case of maximization. By the way, this lesson is prepared for maximization problem, and I will prepare another lesson in the case of minimization. So in maximization, that means our objective is to maximize, or our objective function is maximization. So the first step in this case is convert each inequality means less than or equal to, greater than or equal to, and so on, in the set of constraints to an equality by adding slack variables. By the way, in the case of maximization, we have to add slack variables to make inequality, or to make less than or equal to into equal to. In the case of minimization, we have to add surplus variable on greater than or equal to make it equality. So here, because in the constraint there is less than or equal to, in standardized maximization the constraints are less than or equal to. The constraints functions are expressed with less than or equal to, so we have to add slack variable to make it equal to. And after making standardization, after converting all the constraints into equality, so we have to create initial simplex tableau. After creating the simplex tableau, so the next step is locate the most positive entry of Cj minus Zj. By the way, Cj is the coefficient of the objective variables, whereas Zj is the multiplication or the product of the coefficient of the basic variable with the corresponding coefficients of each constraint. That means after multiplying, we have to add in the bottom row to determine the pivot column. So the third step is to determine the pivot column by finding the most positive entry of Cj minus Zj. Anyway, we will see it with example. And the fourth step is the smallest ratio of right-hand side column with their corresponding pivot column that we have found in step 3 to determine the pivot row. So the smallest ratio of right-hand side column to pivot column become the pivot row. After finding the pivot row, the intersections of the pivot column and the pivot row become the pivot value or the pivot number, we can say. So after getting the pivot value using elementary matrix operation or using elementary row operations, we have to make that the pivot number should be 1. So we can divide the pivot number by itself. We can divide all the rows that the pivot number is found by the pivot number, so we can make the pivot number 1. And using another elementary row operations, we have to make that the other values of that pivot column should be 0. That means we have to make the pivot value 1 and other numbers to be 0 using different matrix operation. So this is what we call pivoting. And the sixth step is check whether we have arrived on optimal solution or not by Cj minus Zj. If all the value in the bottom row, that is Cj minus Zj, is less than or equal to 0, so this is the final table and we have achieved our optimality. If not, if they are not less than or equal to 0, we haven't arrived on optimal solution, so we have to go to step 3 again to determine the pivot column and to iterate the steps again. And the seventh and the last step is from the final table, the linear programming has a maximum solution which is given by the entry in the lower right corner of the table. After we have arrived on optimality, so from the final table we have got the maximum solution which is found at the lower right corner of the table. Let's see by examples. Here is an example for solving the linear problem having 3 decision variables using simplex method. So the example says, find the optimal solution for the following linear programming problem using simplex method. So the solution, as I told you, is maximization. It is maximization. Our objective is to maximize this function, and which is subjected to the constraint that is for x1 for x1 plus x2 plus x3 less than or equal to 30 to x1 plus 3x2 plus x3 less than or equal to 60, and the third constraint is x1 plus 2x2 plus 3x3 less than or equal to 40, where x1, x2 and x3 greater than or equal to 0. So this is a maximization problem, which is expressed by z equals 3x1 plus 2x2 plus x3. It is a maximization objective function, and the problem has 3 decision variables, that is x1, x2 and x3. So we have to solve this problem using simplex method. Let's start from step 1, that is introducing slack variables to make these constraints or the inequalities found in the constraints to be equality. So here, as you see, there is less than or equal to relationship. So we have to add something that is a slack variables on the left hand side to make with the right hand side, to make equal with the right hand side. So let's add x4 for the first constraint, that is for x1 plus x2 plus x3 plus x4, and let's add x5 for the second constraint, that is 2x1 plus 3x2 plus x3 plus x5, and let's add x6 slack variable to the third constraint, that is x1 plus 2x2 plus 3x3, like this. Look here, we have to add the slack variables to convert the less than or equal to into equal to, like this. X4 is added in the first constraints, as you see, and to make equal column with the other, to make equivalent number of columns with the other constraints, we have to add all the slack variables on the first constraints by making the coefficient to be 0. So as you see, in the second constraints, we have added x5 constraints, and in the second constraints, we have added x6 constraints, and on the remaining, we make the coefficient of slack variables to be 0. And as you see, this is the standard form of the constraint that is converted into equality. And you see our slack variables, our corresponding slack variables are x4, x5, and x6 for each corresponding constraints. And the objective function can be expressed as 3x1 plus 2x2 plus x3 plus 0x4 plus 0x5 plus 0x6 equals 8. By the way, as you see, the number of columns of each constraints and the objective functions are equal. That is 1, 2, 3, 4, 5, 6. 6 columns for each constraints and 6 columns for the objective functions. Now we can move to the second step, that is creating simplex tableau. So here our simplex tableau looks like this. As you see here, this is our simplex tableau, and CJ is by the way the coefficient of the objective variable, that is 3, 2, 1, 0, 0, 0, and these are the solution mix, that is x4, x5, x6, or we can say this is a basic variable. These are the basic variable, and this CB is the coefficient of the basic variable. CB is the coefficient of the basic variable. As you see here, these are the coefficients of the basic variable found in the objective function. So 0, 0, 0 are the coefficients of the basic variable x4, x5, and x6. And Zj is found below the rows, below all the rows. So Zj can be obtained through multiplying the coefficient of the basic variable by the corresponding columns of x1 and adding those, we can get the Zj. And the same is true for the all Zj values found here. And Cj minus Zj is calculated by subtracting Zj from the coefficients of the objective function. So here in the table we have to put all the coefficients of the first constraints here, and the second constraints here, and the third constraint is here. And these are the right hand side, by the way. These are the right hand side value, or the constraints. The constants found in the right hand side. So as you see here, we already put all the constraints here. Look, this. The first row is a coefficient of the objective function, and this row, as you see, this row is the coefficient of the first constraint, and the coefficient of the second constraint, and the coefficient of the third constraint. And now, and here we also calculate the ratio, and later we will see it. As I said before, CB is a coefficient of basic variable, and CJ is a coefficient of the objective function. So ZJ can be calculated by using this formula. That means ZJ can be calculated by the summation of basic coefficient of basic variable, these variables, times with the corresponding coefficient this, and we can add this to find Z1. For example, 0 times 4 plus 0 times 2 plus 0 times 1 equal to Z1 here. And 0 times 1 plus 0 times 3 plus 0 times 2 equals here 0. And 0 times 1 plus 0 times 1 plus 0 times 3 equal to 0. And the same is true for the remaining. So it looks like this. This is the ZJ value, and CJ minus ZJ, as you see, can be calculated by CJ minus ZJ. So CJ is 3 minus 0 is here 3, and 2 minus 0 is 2, 1 minus 0 is 1, 0 minus 0, 0, 0 minus 0, 0. So it looks like this. So 3, 2, 1, 0, 0, 0. So after finding this CJ minus ZJ value, so we have to see, by the way, whether it is optimal or not. If all the CJ minus ZJ value are less than or equal to 0, so this table is the last table, or it is the optimal table that we can find the optimal solution. As you see, the values 3, 2, 1 are greater than 0. The CJ minus ZJ value are greater than 0, so cannot achieve or cannot arrive on the optimal solution. So let's move to step 3, that is finding the maximum positive value, of CJ minus ZJ. The maximum positive value of CJ minus ZJ, as you see, is 3. 3 is the maximum value. So our pivot column become X1 column. This column is our pivot column because the CJ minus ZJ value is the maximum, that is 3. 2 and 1 are less than 3. So X1 column is a pivot column, and X1 is an entering variable. X1 is an entering variable, whereas the other variable should be a living variable. And let's move to the next step, that is to determine the pivot row. This is the pivot column, as you see. And now let's determine the pivot row to know the living variable. To know the pivot row, we take the least positive ratio of right hand side. Right hand side is divided into X1 column, or we can say pivot column. Pivot columns are this column. These columns are pivot column, and we have to divide the right hand side value into pivot column to determine the least positive ratio. And these are the ratio. Look, 30 divided by 4, 7.5. 60 divided by 2, 30. 40 divided by 1, 40. among this ratio, 7.5 is the least positive ratio. So the first row is a pivot row. The first row is a pivot row. And here, the intersections of the pivot row and the pivot column is 4. 4 is the intersection of pivot row and pivot column. So it is the pivot value. And x1 is, as I said before, is an entering variable, whereas x4 is a leaving variable. So we have to omit x4 and we have to replace x4 by x1, and the coefficient of the basic variable will be 3 because the coefficient of x1 is 3. So we have to put here, we have to put here, we have to put x1 instead of x4, and we have to put here 3 instead of 0. So we have look this, we have replaced the entering variable, the leaving variable, with the entering variable that is x1, and these are the pivot row, and these are the pivot row. This one are the pivot row, and this one is a pivot column, and the intersections of this pivot row and pivot column are 4. So 4 is the pivot value. And the next step, that is step 5, is to make the pivot value 1 by dividing the row by the pivot value. When we divide this pivot row by 4, the pivot value will be 1. So we have to divide this pivot row by 4. And we have to make the pivot column value, the other pivot column value, to be 0. Using elementary row operations, using elementary matrix operation, we have to make other values. That means other than the pivot value to be 0. So using this operation, that is row 1 divided by 4, we convert row 1, we replace row 1 by row 1 divided by 4. It becomes like this. When we divide the row 1 by 4, it looks like this. And now onwards, using different matrix operation, we have to change, we have to make all the pivot column value to be 0. All the values except the pivot value to be 0. Look the operations. Using this matrix operation, that means row 2 minus 2r1, row 2, this is row 2 minus 2r1, 2 times r1 means 2 times 1, 2. So when we subtract 2 minus 2r1, it becomes 0. 3 minus 2 times 1 over 4, 1 minus 1 over 4, 2 times 1 over 4, 0 minus 2 times 1 over 4, 1 minus 2 times 0, 0 minus 2 times 0. So we replace the second row by r2 minus 2 r1, and it looks like this. It looks like this. So using this operation, we convert row 2. We convert row 2 to make this value 0. To make this value 0. And using the other operations, that is row 3 minus row 1, we can make the value here to be 0. So R3 is the third row minus the first row becomes 0. So 1 minus 1 is 0, 2 minus 1 over 2, 3 minus 1 over 4, 0 minus 1 over 4, 0 minus 0, 1 minus 0, and 40 minus 7.4. So it looks like this. It looks like this. And after getting all the modified versions of this simplex table, so we have to calculate the zj, the new zj value. As I said before, zj can be calculated by the summation of cb, coefficient of basic variable, times the corresponding xn column. And here we can get 3 times 1, 3, plus 0 times 0, 0, plus 0 times 0. So it becomes 3. And we have to calculate like 3 times 1 over 4 is 3 over 4, times 0 times 5 over 2 is 0, 0 times 7 over 4 is 0. So it becomes 3 over 4. And the same is true for the remaining values. So we can calculate using this formula. And the next step is to find out cj minus zj. Cj minus zj can be simply calculated by subtracting the zj from cj. Zj is found in the topmost corner, and the topmost row is cj value, and the last row is here is the zj, so we just simply subtract from cj. We just subtract zj from cj and get the value like this. These are the new values of cj minus zj. And our next step is to check whether it has arrived on its optimality or not. So we have to check whether cj minus zj, all the cj minus zj value are less than or equal to 0. As you see here, the two values, that is 5 over 4 and 1 over 4, are greater than 0. So we haven't arrived on optimal solution. Now we have to go back to step 3. We have to go back to step 3 to repeat the iteration again. So in step 3, we have to determine the pivot column by selecting the maximum positive value of cj minus zj. As you see, the maximum positive value of cj minus zj is 5 over 4 because it is greater than 1 over 4. So 5 over 4 is the maximum positive value of the cj minus zj. So our pivot column is x2 column. This is our pivot column. X2 column is the pivot column, and the next step is to determine the pivot row. The pivot row is, as you remember, the pivot row is determined by dividing the right hand side by the corresponding pivot column. Once we determine the pivot column, so we have to divide 7.5 divided by 1 over 4, 45 divided by 5 over 2, 32.5 divided by 7 over 4. So we get 7.5 divided by 1 over 4, 30, 45 divided by 5 over 2, 18, and 32.5 divided by 7 over 4, 19. So among this value, x2 is a pivot row. Sorry, not that's x5. X5 is a pivot row because 18 is the least positive number, the least positive ratio of right hand side divided by pivot column. So x5 row is the pivot row. And from this pivot row and pivot column, as you see, the intersection value, that is 5 over 2, is the pivot value. And our next step is to find out or to make the pivot value to be 1. Determining the pivot row and the pivot column, as you see here we get the pivot value, that is the intersections of the pivot row and the pivot column, that is 5/2. And the next step is using elementary row operation. We have to make the pivot value to be 1 and the remaining value found in the pivot column to be 0. So we have to make this value to be 0 and this value to be 0 and this value, okay, yeah, the first row here we have to make 1/4 to be 0 and 7/4 to be 0, and we have to make 5/2 to be 1. So as you know, our entering variable here is x2, which is found in the pivot column. x2 is our pivot, our entering variable, and x5 is our leaving variable. The leaving variable is found in the pivot row and the entering variable is found in the pivot column. So we have to replace x5 using x2 and the coefficient of x5 using the coefficient of x2, that is 2. And then after we have to divide all the row values of x2, all the row value of x2 by 5/2 to make the pivot value to be 1, and we get like this. When we operate this row operation, when we conduct this row operation, that means R2 divided by 5/2, we get the new value of R2, that is this value. So when we divide 0 by 5/2, it becomes 0. When we divide 5/2 by 5/2, it becomes 1. When we divide 1/2 by 5/2, it becomes 1/5. When we divide minus 1/2 by 5/2, we get minus 1/5. When we divide 1 by 5/2, we get 2/5. And when we divide 0 by 5/2, we get 0. And when we divide 45 by 5/2, we get 18. We get 18. So we make this value to be 0. No, sorry. We make this value to be 1. We make using this operation, using this matrix operation, we make the pivot value to be 1. And the next step is to make this value, that is 1/4 and 7/4, which is found in the first and the third row, to be 0. So we have to use another matrix operation to be 0, to make it 0 in R1, that is 1/4. So we have to operate 1/4, that is R1 minus 1/4 R2. R1 minus 1/4 R2, it becomes 0. So when we subtract 1/4 minus 1/4 R2, so we put the value. Our objective is to make this value to be 0. And we get the value like this. When we operate this matrix operation, the first row can be converted into this value. And now the next step is to make 7/4 to be 0. To make 7/4 to be 0, we have to subtract R3 minus 7/4 R2. We have to conduct this operation. On the third row, so we get the value like this. And now onwards, we have to calculate the ZJ. Once we calculate calculate all the new values of the matrix. So we have to calculate the ZG using CB times xn, coefficient of basic variable times xn. So when we multiply 3 times 1 plus 0, 2 times 0 plus 0 times 0, we get 3. 3 times 0, 0 plus 2 times 1, 2 plus 0 times 0 becomes 2. And the same is true, we have to multiply this with this and we have to add them, we get 1. And we calculate the remaining value like this, and after that we calculate Cj minus Zj. It's simply subtracting the Zj value from Cj, so we get like this. So we get this, and then the next step is to check whether our solution is optimal or not. Our last row is less than or equal to 0 or not. As you see the row, all the values are less than or equal to 0. All the values are less than or equal to 0. That means there is no value which is greater than 0. So the linear programming problem has arrived an optimal solution. And our maximum solution is found in the lower right corner, that is 45. As you see here, our objective function becomes 45 by x1 equals 3 and x2 equals 18, and the slack variable, that is x6, equals 1. So x1 equals 3, x2 equals 18, and x6 equals 1, and the other slack variables value becomes 0. This is the optimal solution. This is the optimal solution. So this is the end of our discussion, and these are the quizzes that you want to that you have to exercise, that you have to test yourself by solving this exercise. So the first question is, what is the purpose of simplex method over graphical method in solving linear program? So you have to try this, and if there is a problem, you have to write on the comment box and try to solve the following problem using simplex method. It has a 3 decision variables and it is a maximization, so try to solve this using simplex method, and you have to use the steps the steps that we have discussed in this section. And this is also another problem that that is used to check your understanding, so try to check it, try to solve. This is the end of our discussion. So if you have any comment, question, or anything that you want, so you have to write it on the comment box. Thank you for listening. Have a good